Hello all, welcome to my course on methods of adhesion measurement theory and practice. Today we are at lecture 34 and we are discussing about concave head, rigid punch or cylindrical punch having concave head, and here are the different list of references that I am giving you from time to time, and we have taken this last few lectures from lecture 28 including today's lecture from this particular reference by Waters et al. So, you may like to refer to this paper. So, we are discussing about cylindrical punch being pulled again from an elastic half space, and it is something like this. And so, in some cases we have this flat plate we have discussed, and we also discussed about this punch having concave head, and this is the critical pull of load expression that we have derived sometime earlier. And then we have shown that there is an enhancement in the pull of load because of this concave head, and that enhancement has been derived. So, if there is a concave head punch and the crack propagates from the center. So, we have this expression that also we derived in the last lecture. So, today we will like to present some problems to see that how much enhancement happens and what exactly goes on. So, let us see. So, in the same problem in the last lecture, so consider that the average pull of stress that needs to be applied for the flat head cylindrical indenter is 5% of the critical stress of separation of the two adherents, means two adherents are there or two adherents, and then there is a critical stress that this interface can take. So, that critical stress of separation, okay. So, the pull of load, the pull of stress is about 5%, okay, of the critical stress of separation. So, that is what it is. So, find that out if for the concave head the crack will start propagating from the center or from the edge of the area of contact. So, these are the different properties or parameters which are given. So, the question is that given these parameters, and if I suppose apply this pull of load on this punch and then let us say this punch, okay. So, in these two cases let us find out if the crack will start propagating from the edge or from the center, will it propagate? So, that means that if the pull of load required to separate this punch from this elastic half space, okay, if for the edge propagation the load is smaller than the center, the crack propagation from the center, then the separation will occur from the edge only, right. If the pull of load plate this edge is smaller than the center, okay, then it will start propagating from the edge only. So, basically that is the idea. So, pull of load of the flat head indenter was given by this, okay, and we said that the critical stress. So, now this is the so the average pull of stress will be what? So, the average pull of stress, this pull of stress, yes. So, that is equal to this PC, and this is let us say flat plate edge, flat plate, this is the pi a square, right. So, pi a square. So, this quantity have to be found out, and sigma c, that is the critical pull of stress, okay, this is 5% of this is equal to this. So, therefore, we have to divide it by 0.05 into this quantity that we can find out h by pi a square. I hope you get it, that the total pull of load, okay, for this flat plate, that is given by this expression. So, we know what is this value, we have found out also in the last lecture. So, we can find it out again, and divided by pi a square. So, that is the average pull of stress, and this average pull of stress is 5% of this critical, okay, pull of stress that this interface can take. So, that is sigma c. So, therefore, we can actually obtain by like this. This quantity will be therefore 1 by 0.05, and then this is let us say square root pi square here. So, it is pi here, a square means a to the power 4, it is a cube here. So, it is a here, and then this is 8 E star and this is W. That is the expression. So, this is Newton per meter square, this Newton meters, Newton square. Yeah, this is fine. So, this is equal to, so we can actually put down this numbers 0.05 into, okay, I do not have space to write here. So, let us write it here therefore. This is 20 because 1 upon 0.05 and this quantity that you already wrote. So, this is 8 into E star. So, E star is 0.667 into 10 to the power 6 into work of addition is 200 millijoule per meter square, 200 into 10 to the power minus 3 divided by pi and A is 5 millimeter. So, 5 into 10 to the power minus 3. Use your calculator and find it out this value. So, it will come out to be 1.648 into 10 to the power 5 Newton per meter square. 10 to the power 5 Newton per meter square. That is all it come out to be. Okay? So, now this is the sigma c we have found out, and now we will find out that what is the pull of stress or pull of load required for pulling out, so separating this sponge, in which case the crack will start propagating from the center. Okay? So, the crack starts to propagate center from the contact of the spherical head, spherical concave head. That is what we would like to find out. So, that expression we have to find out, and this expression we have already derived. So, that is equal to 16 E star into H minus 2 pi square sigma c, that is 16 here, A here, E star here, and this is H here, divided by 3 minus 2, and this is pi, and this is A square into sigma c we just found out 1.65 10 to the power 5, 6 10 to the 5 Newton. So, if you do all that calculation, it comes out to be 8.13 Newton. So, that is for the concave center. Now, concave edge, so concave head having the edge, okay, that is we have found out. So, that will be about 14.73 into that critical load, pull off load, when the edge crack starts propagating from the edge. Okay. So, that is this value. So, that is 14.73 times when the crack starts propagating for the flat plate case. So, the flat plate case, okay, we can find out. So, that we can find out, that is there already there, flat plate indenter. So, that is case 8 pi E square A cube into W A square root. So, let us find it out. This case, this is 14.73 square root 8 into pi into E star. So, E star is 0.667 into 10 to the power 6 into A cube. A cube is 5 millimeter, 10 to the power minus 3 cube into, this is work of adhesion also should be there. So, this is 200 into 10 to the power minus 3, that many Newton. So, find out, do the calculation. So, like that. So, we can now find out that this value comes out to be 8.25 Newton. So, this is 8.25 Newton. Remember, there is a negative sign here, there will be a negative sign here. So, it is 8.2. Now, 8.25 Newton is actually larger than 8.313 Newton. So, what it means that even before the crack starts propagating from the edge, okay, this critical stress sigma c will be attained. So, the P concave center divided by pi square, that is the average stress. So, that will reach this critical stress, okay, even before this PC or about this pull of load that is attained over here, that is 8.25 Newton. So, in this case, for the data that is given, okay, the crack should propagate from the center, that is all it means. So, the crack will start propagating from the center of the contact, and that is because possibly the H is quite high here, large here. So, that means if the H is decreased, okay, if H is decreased, then this 14 points, that this quantity will also decrease, you see. If this quantity decreases, then this quantity will also decrease. So, we will think about that now. So, let us find out for what values of h the location of the first opening of the crack will cross over from the edge to center, means like now the crack should start propagating, okay, from edge, not the center. So, we like to figure it out. So, what it means is that when these two load will be equal, or rather when this PC concave edge, so that means PC at edge, let us say, I am not writing concave edge, okay, PC edge, that is actually smaller, okay, than the PC at center. Okay. When that happens, naturally the crack will now then start propagating from the edge. So, that is what it is. So, therefore, here let us say this is minus 8 E star A H by 3, and this is minus again, this is 8 pi E star A cube into W A. So, that is for the edge, and that is smaller than, should be, this is 16 A E star by H by 3 minus 2 pi A square sigma C, like this. So, therefore, we can say that this is, so like that. So, now we can write, therefore, this is 24, so it is 8, it is pi E star into H, 8 pi 24, 8 H, that is equal to, so that is will be equal to, this is 2 pi A square sigma C minus, this is 8 pi E star into A cube into W A, like that. So, this is now H, therefore, will be equal to, H will be equal to, let us say it is pi gets cancelled, it is 4 here, it here only E star, and this is sigma C into A square. So, sigma C into A square. So, it is Newton meter per meter square. So, it is Newton per meter square is Newton meter square is cancelled, A square. So, here A should be the A, the sigma C square A square A cube, this is minus, and then you have to divide it by, this is minus here, and here it is 8 pi. So, 8 pi E star, it will be 8 pi E star, and this is here, that is it, and here it is A cube into W A. I hope I have done it correct. So, it is pi A sigma C by 4 E star pi. So, okay, somehow I think I have made a mistake here. So, take it this as the correct value. So, 8 yeah. So, this is pi A sigma C by 4 E star, it was 2 pi A square into sigma C, it was 2 pi A square into sigma C, and minus, this is 8 pi A star into A cube W A, and this is pi star into A H. So, pi star into A H. So, there is a here, it is a here, that A I missed, yeah. So, therefore, it is actually A here, there is a here. So, there is a here, and so there is a, it will be A square here, therefore, A square here. So, therefore, A it will get cancelled. So, the A here and this A will get cancelled like this. Okay. So, finally, it is like this. So, here let us substitute these quantities, these values. So, here it will be equal to, this is pi and A is 0.5 millimeter. So, 5 into 10 to the power minus 3 into sigma C into 1.648 into 10 to the power 6 by 4 into 0.667 into 10 to the power 6, and then it is minus square root of, this is pi into 5 millimeter 10 to the power minus 3 into work of adhesion is 200 millijoule per meter square, 200 into 10 to the minus 3 divided by 8 into E star. E star is again 0.667 into 10 to the power 6. So, this should be the value. So, now you need to use your calculator once again and you can obtain. So, this comes out to be close to 0.9463, 0.9463 mm. So, this is the height at which the crack starts propagating from the edge and not from the center. The height increases, then it will propagate from the center. So, 0.946. Now, we can actually vary this age, okay, over some region, and to see that how exactly this load, pull of load required for crack propagating from the center and from the edge, that varies with respect to age. So, this black line, okay, that defines the load required to pull of load required for crack propagating from the edge. So, you see that for around this value 0.9460 whatever. So, below this, for the height below this, the crack is expected to propagate from the center. Okay. So, what it means is the following, that when the thickness is from the head, the concave head, you see when the concave head height is small, something like this. So, the concave head height is small, okay, then the pull of load required from the center, okay, will also be equal to small, in the sense that the crack, the stress concentration does not reach to the level, okay, that crack should start propagating from the edge. So, it happens when the pull of load from the head, this head increases beyond this quantity, this HC here, let us say, okay, then it becomes easy for the crack to propagate from the center. So, in that case, the crack here, the load is actually now in this portion, okay, this pull of load that is required for the center, for crack propagation from the center, that is actually smaller than the crack propagation from the edge. So, in this regime, okay, in this regime, the crack will propagate because of the edge, concave edge is for the edge propagation. So, this is the edge propagation, and in this regime the crack will propagate from the center. This is the bottom line. Now, what it tells us, that this pull of load, maximum pull of load that is required, that varies with this particular height h. Now, that is also now it means that there is a stress profile, it depends upon the stress profile, how the stress profile is varied. So, for example, the stress profile for this flat punch case, okay, that we know that it will be, the stress becomes something like this when you try to pull it, okay, there is a singularity that is attained. So, stress will become something like this. Now, for this stress profile that varies, that becomes different when we have got this, let us say, this concave head. So, in that particular case, the stress profile will, okay, the stress concentration will become smaller, okay, it will get smaller when you have this, when you have tried to pull off load, then the stress concentration will also become smaller like this. Okay. Now, it is possible that to attain an optimum shape, okay, optimum shape of this concave head, for which this pull of load that will be required will maximize. Okay. So, we can find it out, and that will depend upon not just this height h, but this profile. Remember, so far we have discussed this profile as spherical profile, spherical edge, right, spherical head. Okay. But the more general form will be an ellipsoidal head. So, a spherical shape is a special case of ellipsoidal head, that we agree, right. So, what we like to do is to figure out that what is that ellipsoidal shape for which this pull of load required that will maximize. So, what it means is that the crack, okay, so that will depend upon the the stress profile or the pressure profile at the interface. So, now what kind of profile will lead to this kind of like maximum pull of load? So, now that we can figure out, in the sense that let us say that if this stress profile is uniform, okay, it is uniform. So, when you try to pull off this punch, okay, it so happens that whatever is the shape of this head, because of this pull of load, that becomes uniform. Okay. In that case there is no stress concentration. So that means if the stress, this P0, P over here, small p, okay, that is constant. So there is no stress concentration, or in other word, that the all part of this contact area that shares the load equally. Okay, that is the best case scenario. In that case, this there is no stress concentration anywhere, and so in that case it is possible that we will have a situation in which the pull of load that will be required is maximum. Okay. So, now what is that situation in which case this P becomes equal to P0? Now, that we have studied earlier in some previous lecture, in which case we have remembered that we considered axisymmetric load on an elastic half space and in the frictionless contact, and in that case we considered that P is equal to P0 all through this contact area, and we obtained, okay, what is known as this ellipsoidal profile. This ellipsoidal means this vertical displacement V at z is equal to 0, okay, that we obtain as a function of this elliptic integral of the second kind. Remember that we obtained elliptic integral of the second kind and complete elliptic integral second kind we obtained. So, we will like to see that what did you obtain there, because in that case this pressure, okay, was in that case the pressure came out to be constant. So, what was that particular shape for a given total load? So, let us say total load capital P is equal to P0 into pi a square. Remember that we derived all that, and in that case, okay, in that case what is that shape that leads to this pressure as constant? That is all we will get. So, given a P, that is all we like to figure out, and that we did actually. And remember that we did compression, that means we had loaded this, we had actually considered not this kind of concave but actually a convex head, and that we had used to press against this elastic half space. Okay, now we are discussing actually the opposite case, in which case we have this indenter, okay, this sponge having this concave head, not this convex head. So, the concave head will also have this kind of ellipsoidal shape. That is the point here, because now we are discussing about pulling off this indenter. And so, if we remember, we had obtained this, the deformation profiles we obtained for this particular case, we had obtained it in terms of this elliptic integral of the second kind and E star 4, okay, by pi E star into P0 into A, that is what we had, and then we had the maximum vertical deformation or the convex profile. So, remember that here if we replace P0 by sigma minus sigma, so that becomes, then it will become the pull off case. So, in that earlier case we had discussed about compressing this elastic half space, but here in lecture 11, but here we are discussing the opposite case. So, we have to have a negative sign, instead of P0 we will have the negative P0 or like sigma. So, the shape of this head will look something like this, which this profile is in essence is that elliptic integral which is given by this expression, right. So, here this now the opposite case we are discussing the opposite case, in which case we are trying to figure out that what will be the concave shape, optimal concave shape, and so therefore, the shape of the head is something like this now. And so, we have to figure out, so now the vertical displacement at any point is given by this. So, there is a vertical displacement is this quantity, right. So, from this for the elastic half space, okay, this is the vertical displacement. So, at r is equal to 0, what is the displacement r equal to 0? Now, E, this elliptic integral of the second kind at E0, we know this is equal to pi by 2. So, it is minus, this is P0, this is A here, this is E star, and this is 4 by pi into this is pi by 2, it is 2, it is 2. So, it is actually minus 2 P0 into A by E star. And what is the value at r is equal to A? So, at r is equal to A, that means over here. So, this is again minus, this is P0, this is A E star into 4 by pi, and E at 1 we know this is equal to 1. So, therefore, this is equal to 1 here. So, this is equal to minus of 4 P0 into A by pi E star. So, it is like this. So, now what is the profile of the indenter head? So, profile of the indenter head means that at some location r, so this is say r, okay, from this base, what is this height? So, this height z of r, so that can be obtained as what? That can be obtained as at let us say z, not z, v at z equal to 0 at r minus v at z is equal to 0 and r is equal to a, because I am looking at this height. So, I would like to find out this height. So, that is vertical displacement at any r minus at r is equal to a here. So, therefore, this quantity, so this will be equal to v z r. So, that means it is minus of this is P0 a by E star, and this is 4 by pi and E of r by a, and minus at r is equal to, I just find out. So, minus minus plus here. So, it will be 4 P0 a by pi E star. So, therefore, this quantity will be equal to, this is 4, so it is pi. So, it is 4 pi E star, 4, acha P0 is also there, P0 a by pi E star, right. So, 4 P a P star is, so this is equal to 1 minus 4 by pi, 1 minus 4 by pi. Now, I guess we should write it in the opposite way if we consider from, but it should have come out on its own actually, but anyway we will see. So, the debonding occurs when P0 is equal to minus sigma c. So, therefore, we will write it here, this z of r, that is equal to P0 equal to minus, right. Yeah, now it will be okay. 4, it is sigma c into a into pi into E star, and let us put minus here. So, it is 4 by pi minus 1. So, like this. So, if we have an indenter, okay, whose this concave head is of this particular shape. So, it is 1 minus, this is E by r by a, sorry about that. So, it is 4 pi 0 e. So, it is E of r by a minus 1, sorry about that. Yeah. So, it is like this. So, for this particular head shape, we will have this a pressure distribution at the interface, where it will be pressure distribution is constant with respect to r, and that is expected to give us the maximum pull of load that is required, because the stress concentration will not be there anywhere. So, the crack has to open, okay, whenever this critical stress is reached. So, we apply P. So, P by pi a square is equal to the P0 or minus sigma or whatever. So, when this sigma, okay, that reaches this critical value sigma c, then this crack will open. So, therefore, this is the maximum pull of load that can be attained for this particular shape. So, we will discuss about this issue more in the next lectures. Thank you.